differential equation with the use of eigenvalues and eigenvectors. Now, consider this initial value problem here. Dx over dt is equal to a matrix with these elements times x given our initial condition x0 is equal to 3, 4. Now, this equation here can be rewritten as x prime is equal to ax, where your a is the coefficient matrix and this is your a, and x is a vector. Now, we're gonna use and we're gonna find the eigenvalues and eigenvectors for the coefficient matrix and substitute that to this form to find our solution x of t. Our x of t is equal to v hat e to the lambda t, where your v is just your eigenvector and your lambda is your eigenvalue. Now, let's find first the eigenvalues of this problem. Now, to find the eigenvalues, this equation right here should be satisfied. This says that the determinant of lambda times your identity matrix minus your coefficient matrix should be equal to 0. Now, before getting your determinant, let's first find the lambda I minus a. Your lambda is just simply the lambda, and your identity matrix is 1, 0, 0, 1, minus your coefficient matrix is this one. 4, negative 2, 2, 4. 4, negative 2, 2, 4. And then distribute the lambda to the identity matrix. We have a new matrix here. Lambda 0, 0, lambda. This is because lambda times 1 is lambda, lambda times 0 is 0, and lambda times 0 is 0, lambda times 1 is lambda. And then we'll subtract the coefficient matrix from lambda I. Lambda minus 4 is just lambda minus 4, that's why we have it here. And 0 minus negative 2 is just 0 plus 2 or 2, and then 0 minus 2 is negative 2. Lambda minus 4 is lambda minus 4. Now let's find the determinant of that matrix. The determinant is just multiply these alternating terms here, or elements, lambda minus 4 times lambda minus 4 minus negative 2 times 2. Now we have lambda minus 4 squared plus 4 should be equal to 0, as it says right here. This should be equal to 0, the determinant of the new matrix. Now, lambda minus 4 squared is now equal to negative 4, and then taking the square root of both sides, we have lambda minus 4 is equal to positive negative square root of negative 4. Now, this is just simply 2i because square root of negative 1 is I, an imaginary number. And your lambda now is equal to 4 plus minus 2i. Now, notice that your eigenvalues are, these are now your eigenvalues, and these are complex eigenvalues now. There are cases that you have repeated eigenvalues, repeated values, and there are also distinct ones, and now this example is a complex eigenvalue. Now, to find your eigenvector, we're going to use one of those eigenvalues because either of those two, even if you use either of them, you're still going to have the same results. Now, first, let's find the eigenvector v1 using your lambda 1 4 plus 2i. Now, substitute this lambda 1 to a minus lambda 1i, where your a is your coefficient matrix and your I is your identity matrix. Now, we have here your coefficient matrix minus lambda 1i. It's just lambda 1, 0, 0, lambda 1, and your lambda 1 is 4 plus 2i. Now, subtracting this from this, we have 4 minus 2i. Now, cancel out. We have negative 2i left. Negative 2 minus 0 is negative 2. 2 minus 0 is 2. 4 minus 2i, we have negative 2i. Now, let's multiply this second row here by negative I. To have 2 times negative I, we have negative 2i, and then negative 2i times negative I, we have 2i squared, and your 2i squared is just simply 2 times negative 1 because I squared is negative 1. That's why we have negative 2 here, and we have negative 2i here. And you can subtract row 1 from row 2 and then put the result in row 2. We have 0, 0 in your row 2. Now we can set equation here from your row 1, negative 2i k1 minus 2k2 is equal to 0. Now rearranging to get the value of k1 in terms of k2, we have now k1 is equal to I k2. If your k2 is equal to 1, then your k1 is equal to I times 1. And your k1 is simply I. That's why we have our eigenvector v1 hat is equal to I1. When your k2 is 1, your k1 is I. Now, for the next, that's our first, our eigenvalue, and let's find the second eigenvalue, and I mean eigenvector. Let's find our second eigenvector using our second eigenvalue. Lambda 2 is equal to 4 minus 2i. Now let's substitute the same process to get the equation of k1 in terms of k2. Now this is the result, and you just study this because it's just the same as the previous page. Now k1 is equal to negative I k2 in terms of k2, and if your k2 is 1, then your k1 is negative I. That's why we have an eigenvector of negative I1. You can check that in you can check that above that it's right. Your eigenvector is this. Now to solve for the solution, we can this is what I'm saying, that you can use you can only no you can use just one eigenvalue, and let's use the eigenvalue 1. Lambda 1 is equal to 4 plus 2i, and let's use our eigenvector I1 and substitute that to our solution. X of t is equal to e lambda 1 t times v1 hat. Our v1 is our eigenvector, this one, and our lambda 1 is our eigenvalue. Now we substituted this 4 plus 2i here, and then we actually disintegrate this. E to the 40 times e to the negative e to the 2it is just simply this one. We just disintegrate this, but e to the I times 2t is just equal to cosine 2t plus I sine 2t. That's why we should substitute this value or this expression here to here. Now our x of t now is e to the 40 times cosine 2t plus I sine 2t times our eigenvector I1. Now let's distribute this to each of the terms in our eigenvector. Now cosine 2t times I is just I cosine 2t, I sine 2t times I is just I squared sine 2t, and cosine 2t times 1 is cosine 2t, I sine 2t times 1 is I sine 2t. Now your I squared is negative 1, that's why we have negative sine 2t here, and we're rearranging this so that they'll match or they'll have the same columns. And this one is I cosine 2t. Let's align this with the component with the imaginary number also below, and we now have our solutions, our solution of our x of t. We just get these terms here and put constant term c1 e to the 40 times negative sine 2t times cosine 2t. This negative sine 2t is from here and cosine 2t is from here. Also, we can write plus c2 is equal times e to the 40 times this cosine 2t and sine 2t. We just remove the I or the imaginary number there. And let's solve for c1 and c2 given our initial condition. Our initial condition is just this: x0 is 3/4, and when your t is 0, your solution is 3/4. Then let's substitute 0 here. This is our solution that we got, negative sine 0, cosine 0, e to the 0 here, c to e to the 0 here, cosine 0 here, sine 0 here is equal to c1 times 0, 1, since sine 0 is 0, cosine 0 is 1, and e to the 0 is 1, cosine 0 is 1, sine 0 is 0, and this should be equal to the vector 3, 4. And from this one, we have c1 plus c1 times 0 is 0 plus c2 times 1 is equal to 3. That's why c2 is 3. And c1 times 1 plus c2 times 0 is just simply c1 is equal to 4. That's why we have c1 is equal to 4 and c2 is equal to 3. And let's substitute these constant values above. We have c1 here for 4. And let's distribute that inside. Let's put that inside. And simply add and factoring out the e to the 4t. We have negative 4 sine 2t because 4 times negative sine 2t is negative 4 sine 2t plus, since your c2 is 3, 3 times cosine 2t is 3 cosine 2t, and 4 times cosine 2t is 4 cosine 2t, and 3 times sine 2t is 3 sine 2t. And this is your solution. And that's all.